Welcome to today's paper reading. Today's paper is titled, Composer, Creative and Controllable Image Synthesis with Composable Conditions. This paper was published on AR14 by Lianghua Huang and colleagues from Alibaba Group and Ant Group. The abstract introduces a new approach to generative models that addresses the limitation of current models in terms of controllability. These models, despite their ability to synthesize high-quality images, lack flexibility in controlling the output. The proposed method, referred to as Composer, introduces a paradigm shift by decomposing images into representative factors and training a diffusion model with these factors as conditions. This allows for the recomposition of the input image with enhanced control over aspects such as spatial layout and color palette. During the inference stage, the model leverages rich intermediate representations, creating a vast design space for customizable content creation. This approach supports various levels of conditions, including text descriptions, depth maps, sketches, and color histograms, enhancing both controllability and the versatility of the model across different generative tasks. Generative models, such as those conditioned on text, can now produce photorealistic and diverse images. However, these models often fall short in providing the level of control needed for practical applications. They struggle to accurately produce images with specific semantic, shape, style, and color specifications. The key to achieving more controllable image generation lies not just in conditioning, but more significantly in compositionality. This concept allows for an exponential expansion of the control space by introducing numerous potential combinations of visual components. Figure 1 illustrates the concept of compositional image synthesis. It begins by decomposing an image into a set of basic components, which are then recomposed to create a new image with high creativity and controllability. These components, available in various formats, serve as conditions during the generation process, allowing for flexible customization at the inference stage. This approach ensures that the new images maintain quality and creativity while offering extensive control over the synthesis process. The method involves two main phases, decomposition and composition. In the decomposition phase, an image is divided into a set of independent components, each capturing different aspects of the image. These components include representations such as captions, semantics, style, color, sketch, instances, depth map, intensity, and masking. In the composition phase, these components are reassembled using a conditional diffusion model to synthesize creative and controllable images. This approach allows for the flexible customization of image conditions and the generation of high-resolution images. Figure 2 illustrates the capabilities of Composer in generating image variations and interpolations. In Part A, each example shows a source image in the first column, followed by 4 variations generated by applying different conditions to Composer. These variations demonstrate the model's ability to creatively alter images based on various input conditions. Part B presents image interpolation results. The first row shows the interpolation of all components between a source image and a target image. The subsequent rows display results where specific components of the source image are maintained, highlighting the model's control over which aspects of the image are interpolated or preserved. Figure 3 illustrates the process of image reconfiguration supported by Composer. This involves altering key representations of an image, such as its sketch and segmentation map, to create new variations. The method employs DDIM inversion to obtain the latent representation of the original image, followed by DDIM sampling with modified representations to generate a reconfigured image. The direction of variation is determined by the differences between the original and modified sets of representations, allowing for diverse manipulations of the image. Figure 4 illustrates the process of region-specific image editing using Composer. By incorporating a masked image as an additional condition, Composer is able to focus its manipulation efforts on the region of interest within the image. This capability showcases Composer's advanced functionality in directing image editing tasks to specific areas, enhancing the precision and control over the image manipulation process. In this section, we will discuss the key aspects of our experiments. Firstly, we trained multiple models with varying parameters for different tasks such as conditional image generation and upscaling. Specifically, we used a 2 billion parameter base model for generating images at 64 by 64 resolution, a 1.1 billion parameter model for upscaling to 256 by 256 resolution, and a 300 million parameter model for further upscaling to 1024 by 1024 resolution. Additionally, we trained a 1 billion parameter prior model for projecting captions to image embeddings. Secondly, we explored various image manipulation techniques using our Composer tool. This includes creating variations of images, interpolating between images in the embedding space, and performing image reconfigurations through DDIM inversion and sampling. Lastly, we reformulated several traditional image generation and manipulation tasks using our Composer architecture. This includes tasks like palette-based colorization, style transfer, and image translation, demonstrating the versatility and potential of our compositional generation framework. Figure 5 illustrates the reformulation of traditional image generation tasks using our Composer. Notably, the model is applied directly to all tasks without requiring any retraining, which underscores the potential and flexibility of the proposed compositional generation framework. This approach allows for a versatile and efficient method of image synthesis, demonstrating the capabilities of the Composer in various creative and controllable image generation scenarios. Figure 6 showcases the compositional image generation capabilities of Composer. Each image is generated based on specific conditions listed below it, highlighting the model's ability to create diverse outputs from a combination of textual descriptions and visual elements. This figure exemplifies Composer's flexibility and controllability in image synthesis, demonstrating its potential across various creative and practical applications. Diffusion models have shown significant success in image generation, surpassing GANs and performing on par with autoregressive models in terms of fidelity and diversity. Recent advancements include hierarchical diffusion models, which use one large model for small-resolution images and two smaller models for upscaling. Unlike traditional text-to-image models, our method supports composable conditions, offering better flexibility and controllability. Many recent works have extended text-to-image diffusion models to achieve multimodal or customized generation by introducing various conditions. In contrast, our Composer method excels in compositionality across conditions, providing a larger control space and greater flexibility in image generation and manipulations. The decomposition-composition paradigm presented in this study significantly expands the control space of generative models when conditions are composable. This allows for the reformulation of traditional generative tasks using the Composer architecture, revealing previously unexplored generative capabilities. The Composer architecture is demonstrated to be effective for a variety of image generation and manipulation tasks, utilizing both classifier-free and bidirectional guidance. However, challenges remain, such as the potential downweighting of single conditional generation performance and conflicts when incompatible conditions are used. Additionally, the increased controllability of Composer raises potential risks of misuse, which the authors intend to address before public release. In this section, we will briefly review some key references that have contributed to the field of creative and controllable image synthesis. Firstly, we have models focused on text-to-image generation, such as Analytic DPM from 2022, Muse from 2023, and Diffidit from 2022. These models have advanced the ability to generate images from textual descriptions. Secondly, we look at diffusion models, which include denoising diffusion probabilistic models from 2020, improved denoising diffusion probabilistic models from 2021, and Glide from 2021. These models have significantly improved the quality of image synthesis. Lastly, we mention transformer-based models like CogView from 2021, Taming Transformers from 2020, and Gligen from 2023. These models have leveraged the power of transformers to enhance the compositional and controllable aspects of image generation. The architecture of Composer involves several key components. Firstly, the diffusion process is set to 1000 steps with a cosine noise schedule, and sampling is performed over 100 steps. The model size varies, with configurations at 1 billion, 2 billion, and 300 million parameters. These models have different channel counts and depths, such as 512, 320, and 192 channels, and depths of 3 and 2. Additionally, several hyperparameters are crucial, including a batch size of 1024, learning rates ranging from 1.1 times 10 to the power of -4 to 1.0 times 10 to the power of -4, and a weight decay of 6.0 times 10 to the power of -2. These parameters are essential for the effective training and performance of the Composer model. Table 1 presents the hyperparameters used for the Composer model. The table details the diffusion steps, sampling steps, and model sizes across different configurations. The diffusion steps are set at 1000 for all models, while the sampling steps vary from 100 to 10. The model sizes range from 1 billion parameters to 300 million, reflecting the complexity and capacity of each model variant. These hyperparameters are crucial for the performance and efficiency of the diffusion models, which are sampled using the DPM Solver++ algorithm as specified. In the Composer model, conditioning modules play a crucial role in synthesizing images with specific attributes. The global conditioning module processes global conditions like clip sentence embeddings, image embeddings, and color histograms. These are projected and added to the time step embedding. Additionally, image embeddings and color palettes are projected into extra tokens and concatenated with clip word embeddings, serving as context input for cross-attention layers. On the other hand, the local conditioning module handles local conditions such as segmentation maps, depth maps, sketches, grayscale images, and masked images. These are projected into uniform dimensional embeddings with the same spatial size as the noisy image using stacked convolutional layers. The sum of these embeddings is then concatenated to the noisy image, allowing for precise local control over the image synthesis process. Figure 7 illustrates the global conditioning module within Composer. This module processes various global conditions, including clip sentence embeddings, image embeddings, and color histograms. These conditions are projected and added to the time step embedding. Additionally, image embeddings and color palettes are projected into 8 extra tokens, which are concatenated with clip word embeddings. This combined input serves as the context for cross-attention layers, enhancing the model's ability to synthesize images with creative and controllable attributes. Figure 8 illustrates the local conditioning module of Composer, which processes various local conditions like segmentation maps, depth maps, sketches, grayscale images, and masked images. These conditions are projected into uniform dimensional embeddings that match the spatial size of the noisy image, achieved through stacked convolutional layers. The module then sums these embeddings and concatenates the result to the noisy image, enhancing the image synthesis process with precise local details. In this section, we discuss additional samples that illustrate how Composer handles conflicting conditions. Specifically, Composer tends to give less weight to conditions that are less detailed when conflicts arise. This is evident in comparisons between segmentation maps and sketches or depth maps. Additionally, we present further colorization results, which are visualized at a resolution of 256 by 256 to keep file sizes manageable. Lastly, we show more examples of style transfer, also presented at the same resolution to reduce file size. Figure 9 illustrates how Composer, a creative and controllable image synthesis tool, manages conflicting conditions by showcasing extreme scenarios where conditions originate from different sources. A key observation is that Composer tends to assign less importance to conditions that have fewer details when conflicts arise. This is evident in the comparison of segmentation maps, sketches, and depth maps, as well as text embeddings versus image embeddings. The figure visually demonstrates how Composer prioritizes more detailed conditions to maintain the integrity and coherence of the synthesized image. Figure 10 presents additional colorization results, specifically visualized at a resolution of 256 by 256 to minimize file size. This approach allows for efficient storage and transmission of the colorized images while maintaining a level of detail suitable for various applications. The figure showcases the effectiveness of the colorization process in enhancing grayscale images with vibrant and realistic colors, demonstrating the versatility and practicality of the method in different scenarios. Figure 11 presents additional style transfer results, showcasing the transformation of images while maintaining a resolution of 256 by 256 pixels. This resolution choice is made to effectively reduce the file size, making the images more manageable and suitable for various applications. The style transfer process involves applying different artistic or thematic styles to the original content, resulting in visually appealing and creatively enhanced images. Thank you for watching.